Hello everyone. Today we're going to show you how you can do Acausal modeling and create components with Dyad. We will build a simple RLC circuit from scratch without the use of any external libraries. To start, I'm going to create a Dyad component library. I'll open up the command palette, type out Dyad, and then select Create Component Library. Once prompted, I'll give my component library the name RLC Components. And I'm going to go ahead and save my component library inside of this folder on my desktop. Next, what I'll do here is open up the command palette, type out Julia, and select Start REPL. Here, in the Julia REPL, I'm going to enter the package manager by hitting the close bracket key. And here, I'll instantiate my project. Next, I'll exit the package manager by hitting the backspace key. Okay, so now let's go ahead and create our Dyad components. On the left side, in the Dyad folder, I'm going to go ahead and create a new file. And I'll name this file rlc_parts.dyad. In this file, I'm going to define a connector called pin. This pin has a potential variable V as well as a flow variable I. I'm going to hit save. And then when I do that, of course, a Julia file for the pin's definition is inside of my generated folder. Next, let's define a resistor. Here, my resistor has two pins, a positive and a negative one, a variable V indicating voltage, variable I indicating current, as well as a parameter R for the resistance. And below here, we have some relations that define the physics for my component. And the voltage across the resistor is the difference between the voltage of the positive and the negative pins. The current through the resistor is equivalent to the current through the positive pin. And then the current from the positive pin and current from the negative pin must sum up to be 0. And lastly, we have Ohm's law right here. Next, we'll define a capacitor. The capacitor has a positive and negative pin, variable V and I, as well as a parameter C for capacitance. And then we have these relations down here. The first three are similar to what we saw in the resistor. Then we have this final relation for the capacitance. You might notice that the resistor and the capacitor have some similarities. They both have a positive and a negative pin, as well as variables for voltage and current. In addition, the first three equations in the relations are also identical. Now, in order to avoid repeating ourselves like we do here, let's build up a partial component that we can reuse. So what I'm going to do is I'm going to delete all this code for my resistor and my capacitor. And what I'll do is I will define a partial component called OnePort. This OnePort has a positive and a negative pin, variable V and I, as well as these three relations that we just saw previously. So now using this OnePort, we can define a resistor like so. So this resistor has all the components and variables from OnePort, and as well as all of the relations from OnePort. In addition to everything it's inheriting from OnePort, the resistor also has a parameter R for its resistance, as well as Ohm's law. Similarly, we can define a capacitor like so. This capacitor also extends from OnePort, and in addition to what OnePort provides, this capacitor has a parameter C for capacitance, as well as this relation right down here. And finally, we will also define a step voltage and an inductor and a ground component, like so. Once we've done that, we have all the parts we need to construct an RLC model. So in the Dyad folder, I'm going to create another file called rlc.dyad. Here, I'm going to define a RLC component like so. Our RLC component has a resistor, capacitor, inductor, source, and ground. And of course, these are all instances of components that we previously defined inside of this file over here. Under the relations, we have an initial condition for the current through the inductor, as well as an initial condition for the voltage across the capacitor. And then here we have a set of connect statements which connect our various components together. And this is what enforces the physical relations in between these various components. Next, we'll define an analysis to analyze our RLC model. Here, we're defining an analysis called sim-RLC. This inherits from or extends a transient analysis, and the model that it's using for its analysis is, of course, the RLC model, which we just defined right here. So now that we've defined all our Dyad components, let's go ahead and simulate this model. First thing I'm going to do is I'm going to go ahead and bring in our component library. Next, we will simulate our RLC model by calling result equals sim RLC. Next, we will import the plots package and then plot our results. And there we have it. We have a plot of the voltage across the capacitor as well as the current through the inductor throughout our simulation. So what we did today was we defined various components and connectors for our RLC component. We defined our RLC component itself, an analysis for the RLC component, and then we carried out that simulation and plotted the results like so. Thanks for tuning in.